Hello, this is a second session about a coding interview. On the first one, I made an overview of data structures and algorithms. And today we'll go through several examples of real coding problems. So this is the list of problems we'll go over. And let's start with the first one. So we need to merge two sorted lists. It may be linked lists, like divided here. So each node may have some value and also pointer to the next node, and so on. So we have two lists: a red one and the I don't know what color is it. Let's call it blue one. And then we need to merge them so that the result will be also list will be sorted. We presume that the original lists are sorted already. So each list has a value and it has a pointer to the next. And on the right, we have code of the procedure which does it. So first it checks if the lists are given, and if not given, then just return the other one, whatever, it is just edge case. Then we create the node for the output list. And then what will happen here, we will go through these lists, merging them, and then we'll return the beginning node here, return out. Beginning node in the linked list also called head. So we created it here, then what will happen, we'll put the value. So let's say this value from here, and then we create next node, and we do it in a for loop. And every time we check if one of the lists is ended. So this is the flag which we set if the list came to the end. And also we check which value is bigger, and we put the smaller one. So we continue growing this linked list, right? Well, that's the main idea of the code. It's not difficult. I don't know even if we have to go through it. So we create the list, we point to the head. This is the list of those two nodes. Will we update it here? Okay, we're taking value. Yes, and we update them. We update those values as we travel through the lists. And then we set up flags if we reach the end of the list. At the beginning, they both are set to false. And yeah, and then we just go through this loop. You know what? We have more interesting stuff later. I will put it on GitHub so you can review and maybe even run this code yourself. Just create this class and then you can run this. You will need to populate the list first, of course. Okay, find longest word. So we are given a string of some characters, and we're given a dictionary of words, and we need to find out the maximum length of the valid word, which can be composed from the characters given, right? And we need to return a list of all those long words. So here are some links how to do it. We presume it's all small characters and it's only English. And there are some links where you can see how to do it. And you're not supposed to use any tools which already exist for this, like itertools module has permutations method, which will already do what you need to do. But here is the implementation. And this is, by the way, you can just run it. Like I think I tested it. So it is split in two functions. Well, it's one function can make it. So it returns true if the word can be made from the letters, right? And so That's some simple logic to test it. So at the beginning, and the main portion which we're running here, this is the list of characters. Well, here it says crocodile, go home, but it doesn't have to be meaningful. It's just some set of characters. And here is our dictionary. Well, in this case, the dictionary is very small, right? And what we do for each word in this list, okay, we check if we can make this word, and then we check the length of the word. And if it is maximum length, we add it to the list of words, and then we return the list, print the list of those words. Okay, so again, not a difficult problem to solve. Finding duplicates. Well, standard way of finding duplicates is using a dictionary or a set in Python, which are implementation of hash or hash map algorithm. So this is the standard implementation. How would you do it, right? But this is a specific problem actually from LeetCode, and it's not generic. So they say that you have a list of numbers, and the numbers may be from 1 to n, and each number can appear only one time or two times, no more. And we need to return an array of all integers that appears twice. So the simple way of doing this without even thinking would be like this. So we create an empty list, we create an empty dictionary, and as we go through numbers which are given, if the number is already in the dictionary, that means it's a duplicate. So we append it to the result. Else, we add it to the dictionary. So if, as we go through the numbers, we go first number and dictionary is empty, so we will end up adding this number to the dictionary. And then we'll be adding next numbers, next numbers, next numbers. And then when we get a duplicate, we check if it is a dictionary, it will be appended to the results. And eventually we'll return the results, which is a list of all duplicates. So this is absolutely no-brainer, but here is a clever solution. And again, I got it from LeetCode, and the solution doesn't use dict. And how we determine if we already met this particular integer or not? And the answer is we flip the sign. You see, we multiply it by -1. We change the sign of entry with the particular number. So we're using here the fact that the members of the list are the numbers, and they belong to the same range. So for each number, there is an index. We can go to the position of this index and we can flip the value there. Kind of clever. I would never do something like this in production. I think it's convoluted and a little bit difficult to understand. But you can get something like this on interview, and the benefit here is that it's fast and it doesn't use any dictionary, doesn't use any additional memory. So they wanted big O of n, and it definitely delivers. Okay, next, calculate factorial and Fibonacci numbers. Well, very common. The typical approach may be to use recursion. Like here, for example, we say we return n times factorial of n minus 1. So this is a recursion, right? And similar to Fibonacci, we return Fibonacci of n minus 1 plus Fibonacci of n minus 2. So just a reminder, factorial is multiplication of all numbers from 1 to n, inclusive, and Fibonacci, well, for 0 it is 0, for 1 it is 1, and then next Fibonacci will be the sum of the previous two. So this is how you build next Fibonacci from two previous ones. So this is the recursion, and the problem with recursion is that if you want to do calculations for big n's, well, computers usually are limited in how many recursions you can make, and so better never use recursion, better use a for loop. So here there is example of calculating factorial using for loop. You go in a for loop, well, from 1 to n, well, here it's from 2 to n plus 1, and you multiply on the next number, next number, so you calculate the factorial. And similar with Fibonacci, say current is previous and previous of previous, and then you change what the previous and previous of previous are, and you go through this loop, and eventually you return the final, which is the Fibonacci number. Okay, next one, making coin change. So you're given a list of coin denominations. So here, when we call this function, you can see we give it amount of money and coins which we'll be using. And so given a list of coin denominations, write a function that computes the number of ways to give the change, right? So here is the solution, right? And so let's go through it. So we go through all denominations, and then we start with the higher one, and then we calculate the remainder, and then, okay, I'm confused what's going on here. So we start with the base case that there is one way to create the amount 0. Okay, so n ways of 0 is 0. Okay. Oh, I see. So for each number, so for 0 it's only 1, but then for 1 it will be some number, for 2 it will be some number, and we calculate all of them. So yeah, it's kind of progressively, or well, you can say recursive, but it's more from smaller to bigger, to create the amount 0 and progressively add each of our denominations. The number of new ways we can make a high amount when we account for a new coin is simply high amount minus coin, and this is number of ways which we already calculated before, so we know what it is. Where we know the value already includes combinations involving coin because we went bottom up. Okay, so yeah, so this is the algorithm, and again, I don't want to like go too deep. In order to internalize it, you have to spend time with the algorithm. Okay, so this is how you calculate all the ways how to make coin change. This is another recursive staircase. So you go up staircase and you can do each step, or you can skip one, like make a bigger step. And so each time you climb either 1 or 2 steps. In how many distinct ways can you climb to the top? Well, and it's again, it's very easy. You go from smaller to bigger. It's kind of like Fibonacci, because if you're already on the, let's say, 2 steps from the top, so you can make either one big step or you can make 2 small steps, right? And then suppose you already know how many ways you can do like the previous steps for n minus 2, and then to get here, it will be only one way, and from here only one way, or you can do 1 step. So that's all you do, and it's basically Fibonacci. So the number you get on the top will be sum of two previous numbers. So def climb stairs of n. It is okay. So you, as we go from the bottom, we increase the numbers. So yeah, it's kind of Fibonacci. Okay, let me go to the next one. Okay, balanced parentheses. I actually got this problem on one of the interviews, and it's not a difficult problem, but I challenge you to like look at the code, understand it, whatever, then close the computer, get a sheet of paper and try to solve it. I can try to reproduce it. So what's happening is we're given a string. So we're given something like this, right? And we need to find the longest valid substring. Valid substring is when parenthesis is open, it is closed, and it doesn't have parentheses which are kind of by itself, it's not opened or it's not closed. So for example, this is not valid, or this is not valid, right? And this is valid, and you see the maximum length here is 2. So maximum length here is 4, 6, and here it's only 2 because okay, this is valid, but then everything else it doesn't contribute to a valid string, and so on. So here is the solution, and what's happening here, we're using list as a stack. So as we the valid string should apparently start with the opening parenthesis, and it should end with the closing parenthesis also apparently. So every time we close, we like every time we open, we add something to the stack, and when we close, we go like down in the stack. So here is the logic. We go through the length, and we go up and down, and we check on which level we are, and we calculate the maximum length as we go. Again, I encourage you to just play with this code. In fact, you can just run this, give it this list of tests, and see how it works. So for stack, we're using list, right? And we adding something to the list like this, right? And we removing using the pop. So pop removes from the end of the list. Okay, and the next problem is a famous knapsack problem. So knapsack is a bag, and you have some items which you can put in the bag, and each item has weight and value. So what you want to do, you want to put items so that the total weight of things you put will not exceed the total capacity. So in this case, it's 15 kilograms. But at the same time, you want to get the highest value, like in the bag, right? So the brute force method has time complexity of 2 to the nth power, but it's actually possible to make it much better, linear times complexity. It is described in this link, and this is kind of sort of solution. It's not the totally optimized solution, and it's not possible to understand it from this. You see, it's simple, but in order to understand it, I have to show like about 10 pages of explanations. So let me, oh, maybe I have it open. No. Oh, here. Yep, I have it open. Okay. So this is the problem. It's called 0-1 knapsack because for each item you make decision whether to put it there or not. There are variations of this problem where of each item you can put several items. But here it's 0 or 1. So yes or no for each item. So here is a simple example. So items are apple, orange, banana, and melon. Each one has weight, like 2, 3, 1, 4, and each one has value, 4, 5, 3, 7, right? And the total weight capacity of knapsack is 5. So you try different combinations, and you find that banana and melon total weight is exactly 5, and total like value profit is 10. It's the largest. So this will be the solution, right? Is the best combination, give maximum profit, and the total weight doesn't exceed their capacity. Okay, so again, it's 0 or 1 for each of the objects. That's the decision we need to make. Each item can only be selected once because we don't have multiple quantities of item. Okay, so the brute force solution is very, very simple. So let's say we have 4 items, A, B, C, D, and they have their values and weight. And we build the tree as follows. So we decide, do we take A, we go here, or we skip A, we go here. And then we do B and C and D, and we end up at the bottom. And for each one, we check if we exceed capacity, then it's not good, it's red. So all these things are red. And then if we haven't exceeded capacity, it's green, it's possible. But then out of all the greens, we need to select the one which has maximum profit, maximum value. Okay, so we can do that, and we can build the tree and then go through these and find the maximum. And the complexity of this, given the number of elements, in this case, we have 4, A, B, C, D, so n equals 4. And we do divide, divide, divide. So it's 2 to the nth power kind of complexity of this brute force approach. Okay, this is recursive implementation of this approach. So time complexity is big O of 2 to the nth power, and space complexity of n. Then we analyze this approach, and we see what may happen that in different portions of the tree, we may have actually the same set which we selected, and we will need to continue to do the same calculations. So the question is why we need to duplicate our effort. Why can't we memorize? It's called memorization. It's also called dynamic programming. So instead of repeating the calculations here and here, once we calculated it once here we can just reuse the results. Okay, so this is called memorization again, or it's called dynamic programming. And here the algorithm which does that. So it's top-down dynamic programming with memorization. So it's the same recursive brute force, but we're just memorizing something. And by doing this, we improve our time complexity, which is good. But we can do better, because what we can do, we can change the direction from top down to bottom up. And as we do so, we will populate an array with the possible value which we can achieve. So here is the capacity, the total capacity in our problem. Just to remind you, where is the statement of the problem? Here, capacity is 7, and we have 4 with the profit 1, 6, 10, 16, and weight 1, 2, 3, 5. Okay, so here they are: profit 1, 6, 10, 16, weight 1, 2, 3, 5, and possible capacity can go up to 7. So we start with 0 when we put nothing, and then we start adding and see what kind of profit we can get. And as we're adding to the next layer, what we get depends on the previous layer. So this is kind of simple way as we're progressing through the layers and see what we can get here. Okay, then this is the procedure which implements this algorithm, and our desired result is this bottom right corner. So the maximum profit we can get is 22. Okay. Next approach is when we're trying to analyze how we go through these layers. What we can do, we can optimize the approach, and we can actually realize that every time when we're moving from layer to layer, we don't need, like if we're moving from here to here, we don't need all these previous layers. We don't need all these, we don't need the whole two-dimensional array. What we need is only 2 levels. And from previous level, we create the next one. So instead of big two-dimensional, we can reduce it to have only 2 rows. But then we can make it even better, because what we can realize, we can use only 1 row, 1 array, but we have to be careful in which direction we're updating it. And so once we do this change, this is the final algorithm, and the time complexity is big O of n times number of elements times capacity. Space complexity is just the capacity, and yeah, that's it. And again, I don't want to go through all the nitty-gritty of logic of all this code, because it will take more time than we have. But I encourage you to look through the code. But by the way, if you go on my GitHub and github.com Selector, and I have this special repository called interview prep. Come on. Okay, computer is slow, I guess because of the presentation. Interview prep. And then you go into coding miscellaneous. So here are the examples. Through the next sessions, I will go through many of those examples. And here I have code which you can simply run. So I add txt to the end of the files, but well, you can look at them, just change the extension, run as a Python code, or sometimes it's code in Go. Anyway, this is it for today. I will stop recording.